Normalization is an important tool that allows us to validate and improve logical database design. E.F. Codd first proposed this process in 1972. The term normalization, as defined by Codd, refers to a series of tests performed on relations that determine whether a given relation satisfies or violates the requirements of a normal form. This definition initially applied to three normal forms: the first, second, and third forms. In 1974, however, an even stronger form of normalization, the Boyce-Codd normal form, was introduced. And in 1983, additional forms such as the fourth and fifth normal forms were introduced. In this session, we will be working with the first, second, third, and Boyce-Codd normal or BC and F forms. But before that, we must explain the overall purpose of the process of normalization. Most importantly, the normalization process produces a set of well-structured relations while minimizing data redundancy and data anomalies. We begin with a discussion about data redundancy and anomalies in order to facilitate an understanding of the need for normalization. We also introduce material on functional dependencies, which help us to identify relationships among attributes. These relationships can then decompose relations into newer set of relations that exhibits the properties required by the normalization process. One of the problems in database design that must be addressed is called data redundancy. Data redundancy is having duplicate data in the database. It increases use of disk storage. It reduces efficiency of data updates. Here we show example of data redundancy in this table called student. We see that the department name ISE with address Will Hall and the department logo ISE.PSD are redundant. Database anomalies. Relations with redundant data may cause additional inconsistency problems known as anomalies. Here we show the vet office relation, for example. The vet office has the following attributes: client ID, client name, pet ID, pet name, pet weight, vet ID, and vet name. So in this example relation, vet office, we can see any data redundancy. However, there are still problems with this relation. For example, that is the insertion anomalies. This occurs when a record is inserted into the relation. For example, if there is a new veterinarian that is hired in the vet office, so we may want to insert the record of one vet. However, in this relation, if we insert the record of the veterinarian, such as its vet ID and vet name, there will be problems with the inconsistency of our record, since the client ID and pet ID are our primary keys and which are required. So that means we can't insert a new vet information without the information of its client ID and client name and the pet ID and the pet name. So that is the problem, or one of the problems in this relation. We can't insert a new record for the veterinarian. The problem with insertion is what we call call the insertion anomaly. And we also have a problem here that is related to deletion anomaly. So that will occur if we want to delete a record or some data into or from this relation. So for example, if we want to delete the record of our client Vernon, which is client ID 4519. So if we delete this record, a veterinarian will also be deleted, which is vet ID 31 and vet name John. And that would mean that the the deletion of the client name will lead to the deletion of the record of the veterinarian, which is which would create problem or inconsistency to our data. So another problem that is encountered in the database design is called the update anomaly that will occur if we are to change or update a record in our relation. So for example, if we want to change the weight of one pet, for example, if we want to change or update the weight of a specific pet, then that would mean that we need to change all the weights of that specific pet. So that is that may sound simple, but it can actually produce problems, especially if there are many records that needs to be updated. So if there are instances that one or more records were not updated, so that would also produce inconsistency to our data. Functional dependency. So functional dependency is very helpful in the process of normalization. So we will talk about functional dependencies and the different types of functional dependencies. So functional dependency is a relationship among attributes. An attribute B, for example, is functionally dependent of attribute A if given a value of A, value of B is uniquely defined. It is denoted as if A, then B. Or if given the value of A, we can determine the value of B. Each valid value of A maps exactly to one value of B. And normalization is based on the analysis of functional dependencies within a relation. So it's very important that you understand and you know how to identify functional dependencies in one relation. So here we have an example of again the vet office relation. What are the functional dependencies for the vet office relation? These are, if given the client ID, we can determine the client name, the vet ID, and the vet name. Another functional dependency is, given pet ID, we can identify the pet name and the pet weight. Given the vet ID, we can determine the vet name. Given the client ID and the pet ID, we can determine the client name, the pet weight, the vet ID, and the vet name. And lastly, if we have the value of the client ID, the pet ID, and the vet ID, we can determine the client name, the pet weight, and the vet name. Determinants. Determinants are the attributes on the left-hand side of the arrow in a functional dependency representation. For example, the client ID, the pet ID, and the client ID, pet ID are the determinants in our previous example. Here, the determinants are highlighted in yellow. So you can see that the determinants are those attributes on the left-hand side, on the left of the arrow. If all attributes appear in the functional dependency representation, then the determinant is the super key. This helps in finding out the primary key for the relation. The client ID and the pet ID is the minimal super key and hence is selected as the primary key. We will show how it is selected in the next slide using the dependency diagram. So here is an example of the dependency diagram for the vet office relation. A dependency diagram is a pictorial representation of our functional dependencies. So for example, here from our vet office relation, we can have the functional dependency number 1. In this example, in functional dependency number 1, we can notice that the client ID is the determinant, and this will determine the client name, the vet ID, and the vet name. And in functional dependency number 2, we illustrate using the diagram that the client ID and the pet ID are the determinants of client name, pet weight, vet ID, and vet name. Types of functional dependencies. A partial dependency is a functional dependency in which a non-primary key's attributes functionally depend on a part of, but not all, the primary key attributes. So, for example, in this dependency diagram showing functional dependency number 1, this shows that the client ID and the pet ID as our primary key, but one functional dependency shows that the client ID determines the client name, the vet ID, and the vet name. And in functional dependency number 2, we can see that the vet ID determines the vet name. So, our partial dependency is the first functional dependency, or the functional dependency number 1. So that is because the client ID is just one of the primary keys. Again, the primary keys are the client ID and the pet ID. So only one of the two is the determinant. So this is called the partial dependency. However, in the transitive dependency, it is a functional dependency in which none of the attributes involves attribute of a primary key. So, as shown in the diagram, the vet ID is not part of the primary key. So, vet ID determines vet name is a transitive dependency. Again, if the determinant is not part of the primary key, that is called the transitive dependency. On the other hand, if the determinant is part of the primary keys, then that is partial dependency. Forms of normalization. We will be using the different types of functional dependencies later on while transforming unnormalized form to normal forms. First, we'll have to transform the unnormal form to first normal form, or 1NF, then to second normal form, to third normal form, to boys-cod normal form, or BZNF, the fourth normal form, up to fifth normal form. First normal form. A relation is said to be in the first normal form if each cell in the relation contains exactly one value. So, as shown in the table in this slide, we can see that one cell, specifically for the client ID 2173, it has multiple values for pet ID, which are 1, 2, 3. It also has multiple values for pet name and pet weight. So this is an example of unnormalized form. So how do we transform this to first normal form? In order to transform this unnormal form to first normal form, we need to include values for the client ID and client name, vet ID and vet name for each of the values that are inside the cell having multiple values. So this is now the first normal form. Previously, 1, 2, 3, or the pet ID 1, 2, 3 in the first 3 records of our vet office relation are situated in one cell. Now, it has their own client ID, client name, vet ID, and vet name. Now, we could see that each cell has only one atomic value. Second normal form. A relation is said to be in the second normal form if it is already in the first normal form and it has no partial functional dependency. Example, the relation from previous slide is in first normal form, but the following partial dependencies do exist. The client ID determines client name, vet ID, and vet name. The pet ID determines pet name and pet weight. Now, we will have to decompose the client relation into smaller relations to remove the partial functional dependency. We will show this in this illustration. This is our first normal form and the dependency diagram of our first normal form, showing that client ID and pet ID determines the client name, the pet name, the pet weight, the vet ID, and the vet name. So from our first normal form, we determine that the partial dependency is that the client ID determines the client name, the vet ID, and the vet name. We also have a transitive dependency, which is the vet ID determines the vet name. Now, for the second normal form, we need to remove this partial dependency. This is our partial dependency, and this is our transitive dependency. So, to remove the partial dependency, we have to create a new relation out of this form. This is now our new form, having the client ID. Okay, you just copy. We're just copying here our partial dependency. The client ID determines the client name, the vet ID, and the vet name. Okay, and we also copy the transitive dependency. So we have here the vet ID and the vet name. Now, the next is to determine those attributes that do not belong to the partial dependency, and those are um, the pet name and the pet weight. So their determinants are the pet ID and the client ID. Okay, because this is our functional dependency client ID, and pet ID determines the client name, the pet name, the pet weight, and the pet ID and the vet name. However, the client ID, the client name, the vet ID, and the vet name were already included in the first relation. We'll call this the client relation. So we will now include in the second relation. We will name this the pet relation, having the client ID and the pet ID as our primary key and determinants. So they both determine the pet name and the pet weight. So this is our new attributes for the second relation. From the first normal form only having one relation, it now has two relations, the client relation and the pet relation. Third normal form. A relation is said to be in the third normal form if it is already in the second normal form and it has no transitive dependencies. So previously in the second normal form, we remove the partial dependency. This time, we remove the transitive dependency. So we consider again the example in our previous slide, which is the client and the pet relations. The client relation has a dependency. The vet ID determines the vet name. So now we will have to decompose the client relation further for smaller relations. So we will show this in the next slide. So for the illustration, we have here our second normal form in our previous example using the client relation and the pet relation. The client relation has the client ID, determines the client name, the vet ID, and the vet name. And the client ID is the primary key and determinant. We also have vet ID determines the vet name. Pet relation here has the client ID and the pet ID determinants, identifying the pet name and the pet weight. To transform this into third normal form, we have to remove the transitive dependency and create a new relation. Here, the transitive dependencies are enclosed. Now we enclosed here the transitive dependency. The vet, which is vet ID, determines the vet name. This is our transitive dependency. So we create a new relation for that. This is called the vet relation. So the name of the relation has to be related to the names of the attribute. So since that transitive dependency pertains to the record of your veterinarian, so we can name the relation as vet relation. Now, the primary key of the vet relation should be vet ID. and the vet ID determines the vet name. So these two columns or attributes will be our or these two will be our attributes for the vet relation. We are still retaining the vet ID here, okay, to show the relationship of our client relation and our vet relation. So we retain the vet ID, which becomes now a foreign key. Next is we have the pet relations are the same. Okay, it does not change since there are no transitive dependencies. So we just copy the pet relations in the third normal form. So again, in our third normal form, we remove the transitive dependency. This is the transitive dependency, and we create a new relation for the transitive dependency. We now have three relations: the client relation, the vet relation, and the pet relation. Next is the boys-cod normal form. Functional dependencies related to candidate keys may also cause data redundancy. A relation is said to be in boys-cod normal form or BCNF if it is already in third normal form and every determinant is a candidate key. Let's take a look at this example. Since our client, vet, and pet relation do not include are already in the normal form, we'll take a look at another relation. In this example, we use the student relation. Here, the student relation has the attributes student ID, major, advisor, and major-GPA. So this means that the student ID and the major determines the advisor and the major GPA. We also have here a functional dependency, which is advisor determines the major. So here in this example, a student can have many major, and each major should have an advisor. And one advisor or an advisor should only takes should only handle one major. So that means one advisor determines a major. Relation is already in third normal form, but there are still anomalies. Update anomaly if there is a change in advisor. For example, if the advisor of a specific major is changed, then that means we need to update all of the records for that specific major. We need to update its advisor, and that will cause us inconsistency if we can't be able to update all of the records of the advisor for that specific major. Another problem is insertion anomaly. If, for example, if a new advisor is added, we can't be able to add that advisor if there is no student assigned to that advisor. Another problem is the deletion anomaly. If the student is removed and if an advisor has only one advisee, then that would mean the advisor will also be deleted. Here, we have the advisor determines the major has its determinant as a non-candidate key. As we can see, the functional dependency number 2 in our dependency diagram shows that the determinant advisor is not a candidate key, or it's not also part of the primary key. The solution to that is we have to change the primary key. From student ID and major, we need to change it to student ID and advisor. But this does not help much. The dependency now becomes a partial dependency. However, we can fix the partial dependency by applying again the second normal form, the process of transforming to second normal form and third normal form again. Example, this is the student relation before BC and F. The student ID and the major determines the advisor and the major GPA. In BC and F, we have to change the advisor and the major so that the advisor becomes a candidate key or part of the primary key. Now, we have this advisor and the student relation in BC and F. We remove this part because it will become advisor here. We will have to change this to advisor, and this one will be major. The primary key are student ID and advisor, and the advisor determines the major. This will become now a partial dependency. And going back to the second normal form process, we have to remove the partial dependency. That is why we now have a new relation for our partial dependency, and that is the advisor determines the major. And the remaining relation or the remaining attributes of our relation would be the major, GPA, and the primary keys, student ID and advisor. Because we already removed the advisor and the major, we now have the student ID, the advisor, our primary keys, and the remaining attribute is the major, GPA. So we now have two relations in the BCNF form, the student relation and the advisor relation. Principles for good database design. Relations in a well-designed database meet the following criteria: no redundancy, no partial dependencies, no transitive dependencies. Guidelines: identify entities involved in their relevant attributes and identifiers. Define relationships between entities. Draw an ER diagram to model the problem. Transform the ER model to a relational schema. Normalize the relations up to B, C, and F.